Um, Good afternoon, everyone. I hope everyone can hear me in the back. My name is Patricia Gonzalez-Guerrero. I'm a research scientist at Lawrence Berkeley National Laboratory, and with George Michelogiannakis, we are co-leading the HPC and AI modularity workstream. We just launched it, I think, at the end of August. And the idea for this workstream is to make the case for the standardized chiplet form factors to deliver specialization and heterogeneity for high-performance computing and artificial intelligence. Why? Why is this important? Well, I don't know if you guys, I imagine you guys have seen this plot before, but you can see that average performance improvement was really good for some time, and then it went down dramatically. So there are multiple reasons for that. One of them, of course, is the challenges of scaling down transistors, but there are others, many others that are also important, such as limitations in power consumption, the fact that interconnect doesn't scale at the same rate that transistors, the excessive cost of moving data from processing units to computing units. And this is important. Keeping up with performance improvements over the years is very important, because with HPC, we're trying to solve pressing issues. And by pressing issues, of course, we talk about manufacturing and semiconductors and EDA and all the things that keep our economy going. But we're also talking about solving pressing issues for humanity, such as energy generation and distribution, which is a big one for us right now. And then something like weather modeling, that is, you have seen it in the news for the last couple of weeks for what is happening on the East Coast. So the other problem that we're facing today is that artificial intelligence is hungry for computing performance. So when we were talking, like, we first did a projection, and this was before artificial intelligence was a thing. We were thinking that the consumption, energy consumption, was going to double every 3 years. And that was already problematic. We were seeing effects and negative effects in our economy and people, how people live their lives. But now, with artificial intelligence in the horizon, we see that power consumption doubles every 3 months. So if it was problematic before, now it is kind of really dramatic. So, okay, so the good news is that there are many ways for getting HPC and artificial intelligence back on track. So we can look in the y-axis, and there is a lot of work in new devices and materials. And then in the x-axis, we can look into new architectures and packaging. And as you can see, is that if we look at the top of the technology, there are many ways when we look into software, algorithms, and hardware architectures where we can still get the performance that we need for HPC and AI. And one in particular that is exciting for me, and I know a lot of you, is domain specialization. So the thing with the specialization is that it already exists. It's abundant there. So you can see, for example, here an example of an Apple architecture with at least 40 specialized blocks. And you can also see on the other side the vision for Facebook, where they have on the bottom the early compute area, where everything was standard and everyone used the same. But then when we look into how modern computation should look like, you see hardware, pieces of hardware specialized to do one thing really, really well. Even be that thing machine learning or cognitive security or autonomous vehicles. Like a piece of specialized hardware to do one thing very, very good. Okay, so how does specialization look for HPC and AI? Since we work in HPC in Lawrence Berkeley National Lab, we have a couple of ideas of how we would like to do this. So basically what we argue is that we can have scientific accelerators placed next to computing cores. So here I'm showing you an example where I have an array of RISC-V cores, open source, and then next to it I can have accelerators that are generic. I didn't place anything there because it's like that's something that is under investigation. But we have seen 100 to 1,000 times performance acceleration, performance improvement when we evaluate, for example, to place fast Fourier transform accelerators next to the RISC-V cores, general matrix multiplier, and that is also something that is valuable for artificial intelligence. Some graph analytics, so when we have accelerator hardware for graph analytics, that's also very valuable. And then engines for fast compression and decompression to address some of the memory bottlenecks that we are issuing now. So that's when I get really excited, but as promising and exciting that this is, HPC alone won't drive specialization, although we saw that the keynote speaker said that we had, on the first day of the OCP Global Summit, he said that we need to build more El Capitan and more Frontier, so I don't know if, hopefully this changed, but the thing is that HPC alone won't drive specialization, so although it moves a lot of billions, is still not enough to drive this specialization to the market. So, and that's when it's really exciting because chiplets can solve that issue. So chiplets modularity is a promising solution for HPC, and this is very in line with what Arvin was saying some minutes ago. But the idea is that if you get a monolithic SoC, that is the way that we build systems today, and then we get all the pieces that are necessary to build this monolithic SoC and find what are the modules that you need to build this system on chip, you can have this chiplets marketplace that is very promising for a lot of us, the hyperscalers, but also the startups. And then with these modules, you can take these modules from the chiplets marketplace and build different variants of a system. So here there is an example where you can have one for artificial intelligence and machine learning, like Arvind was saying, or one for networking, or one for servers, or one for PC, right? So all these enabled by advanced packaging heterogeneous integration, of course. So here is a concrete example that I think is very inspiring that John and Bapi did some time ago, and there is a paper out there. And this is the thought experiment that they did with the Fugaku system on chip. So the first step to do this is find what are the specifications for the Fugaku SoC. And then they find things like die size, power thermal, aspect ratio, number of cores, how do the modules communicate, system power, and so on. So they kind of had very clear what were the specifications that they were targeting. And then they said, okay, these are the type of chiplets that we need if we wanted to build the same architecture that we had in Fugaku. So here, so we have, I think, 1, 2, 3, 4, 5, 6 different chiplets, or 5 different chiplets. And then with these 5 different chiplets, you could build an analogous of the Fugaku SoC that we had before. And then they find what are the attributes of these different chiplets. So this is kind of an educated guess of how these chiplets would behave, or the form factors and specifications for each of these chiplets. And this is quite interesting, of course, and quite nice, but what is exciting to me, or when that's how they got me hooked into this, is the idea of that you can put specialized hardware accelerators to build different architectures, and that's what it becomes really promising for HPC and artificial intelligence. So here is an example how the chiplets marketplace can enable the different variants that we have. So here I'm showing, first we have the baseline architecture that is very similar to having the monolithic SoC for Fugaku, and then we can replace some of the computing units and then replace it with, for example, FPGAs to have some programmability. We can replace it for an inference engine or for a sea of RISC-V cores, or in the case of a specialization, then you could have a future accelerator. And the idea is that this chiplet that is going to be placed there has to be compliant with size, power, and thermals. So if this happened, like if we are able to put this together, then a lot of opportunities come up. So if someone comes and tells us, okay, so if you have a space in our chiplets platform, what kind of a chiplet for science would you place there? So of course there are a lot of options there, but one of the most I guess, an example for a scientific kernel is fast Fourier transform. I think this is something that we are all familiar with. But then the idea is that the fast Fourier transform is a major kernel for solving a lot of problems such as density functional theory or molecular dynamics or signal analysis or image processing. For example, in particular for density functional theory, that is 25% of the DOE workload. It makes sense to try to tackle that problem. So what we find is that the FFT hardware accelerator can help or can deliver 50 to 100 times better efficiency than a GPU, which is one of the most powerful processing engines that we have today, right? Okay, so to get back to the work stream, I hope you guys get excited and join us. So we are a very new work stream. But the idea here is that we want to develop open standards, that is the integration of chiplets from multiple vendors into future systems, and thus also support reusability of hardware IP for HPC and AI applications. And that kind of gets along the same lines of the two previous speakers that were talking about the challenges of integrating all these chiplets from different vendors. And then we want to be able to suggest the technologies that support this modularity and accelerate scientific and AI workloads. So basically what we want to do in this work stream is provide a path to achieve chipless modularity for AI and scientific applications. We have divided our work into phases. So the first one is that we want to identify specialization opportunities. So basically, the first task is to identify the HPC compute kernels that are important for science and occupy large fractions of time and resources in today's HPC system. We need to do the same for artificial intelligence because, as you notice, HPC and AI kind of go hand in hand. And I think AI is transforming the computing system more towards what HPC looks like today. And then we want to identify memory and communication requirements for the identified kernels. And then we're going to take a look into supporting technologies. And this is going to come later. So we are on phase one because we just launched the work stream. But once we have phase one kind of mature, we are going to be able to get into technologies and standards and identify what is it that we need to make modularity a reality. So to finish, I want to tell you that we want your participation. We really want your input. We want to understand how, what do you think about how to achieve this modularity. So we have a wiki. So here is the code. So in the wiki, you can subscribe to the project mailing list, add the meeting to your calendar, and please, please join the conversation. We're very eager to hear you. So with this, I'm going to finish here. Thank you.
Thank you, Patricia. Any questions for Patricia?
I'm wondering if there are efforts to bring like network PHYs closer, like photonics engines closer to like general purpose processors or accelerators, kind of like what they're doing with switches with CPOs.
I think that's a quite promising technology, and that definitely will be part of phase two, where we want to make sure that we include all the possible technologies that would make this chipless modularity a reality. So yeah, so at some point we're going to have to look into it and make it part of the conversation. So if you work on that, please join us.
I wish above my pay grade. I wish you luck.
Thank you so much, Patricia. Next, we have a panel. So it's going to take a few minutes to set up. I would request all the panelists and John to come to the front.